organized by IIT Delhi and Johns Hopkins, where we talk about scientific machine learning problems. And today we have Dibakar Roy Sarkar. He is currently a PhD student in the Department of Civil and Systems Engineering at Johns Hopkins University. He has earned his master's degree under the guidance of Professor Chandrasekhar Anavarapu, sorry if I misspelled his name, in geotechnical engineering from IIT Madras. He holds a bachelor's degree in civil engineering from the Central Institute of Technology, Kokrajhar. He was awarded the Tata Motors Excellence Scholarship during his master's studies and the Creel Family Engineering Fellowship in his first year of his PhD. His research interests are in the areas of computational mechanics, scientific machine learning, and PDE control. In fact, that is what he's going to talk about today. And one of the main long-term focus is to build robust and data-efficient AI frameworks for complex engineering problems. So today he's going to talk about learning to control PDEs with differentiable predictive control and time-integrated neural operators. So with that, thank you, Dibakar, for actually giving this presentation. You can now start your presentation.
Yeah, thank you so much for that wonderful introduction. Good morning, everyone. Thank you for joining in. My name is Dibakar Roy Sarkar, and I'm a PhD student at Johns Hopkins University, working with Professor Somdatta Goswami. The paper I will be presenting today is a joint work with my advisor and with Jan Dargona, whose differential predictive control framework sits in the heart of this paper. And it's currently under review at Conference of Decision and Control. The title is Learning to Control PDE with Differential Predictive Control and Time Integrated Neural Operator. And over the next hour, I will talk about talk you through a question that cut across engineering, physics, and machine learning. And the question is, can we teach a neural network to steer a physical system, a fluid, a temperature field, a population of cell, anything that governed by a partial differential equation, fast enough to be useful in real time, accurate enough to be trusted, and generalized enough that one trained policy can handle a distribution of scenarios? The classical answer, model predictive control, say yes, but at the cost of solving a large optimization problem every single time step. And our answer is to move that optimization offline, bake into the training of neural controller, and get the optimization solved once and for all. And I will show you today when it works dramatically well, about 4 order magnitude faster at inference time with accuracy that either matches or even in some cases you will see even beats the classical nonlinear MPC. And the next hour is structured into 4 parts. First, the background, PD, control, and what makes this combination genuinely difficult. Second, 2 machine learning building blocks, the neural operator for the physics and the differential predictive control for the policy. Third, the full method and how these pieces fit together. And the fourth, 3 experiments on canonical PD, which have like the examples I will show are heat equations, Burger's equation, and Fisher KPP, reaction diffusion. And where we put this method into action. Let's get started. Before I get into any methods, I want to ground the conversation by showing uh, uh, 4 real example of the learning-based control in action. And they span across different physical systems at different scales, but they have a very common thread at its heart. And I will show you this 4 because in the next 4 hours, that's exactly like our work exactly fit in this landscape. In the top left, the trajectory tracking optimization for dynamic system. This work by Jan Dargona and collaborators. And you have some nonlinear dynamical system with few state variables, and you train a neural network offline to produce some control actions, which are these bottom plots that track the reference trajectory. And in this case, the reference trajectory looks like a stabilization problem, is going to 0. I'm starting here deliberately because the core work my paper builds on are differential predictive control. And it was first demonstrated by Jan and collaborators. And our paper in one sentence is an extension of this framework from PD to OD systems. In the bottom left, these are m- path planning and control. This is taken from Boston Robotics. And this is more applied cousin to the first example. The neural policy has to be fast enough to actually drive the leg robot or the manipulator in real time. Uh, and if the robot runs at 100 hertz, you can't afford to solve a nonlinear optimization every 10 milliseconds. So you train a policy once and offline and then deploy it. And this is why learning-based control has been essentially applied in the modern robotics. In the top right, is one of the most ambitious demonstration to date. It's DeepMind and EPFL's tokamak plasma shape control published in Nature in 2022. This is governed by magneto-hydrodynamic equation, which are coupled nonlinear PDEs. And they trained a neural network using deep reinforcement learning to drive 19 magnetic coils that shape the plasma in real time. And the figures show several exotic configurations that the train policy actually holds, including some snowflake, like you can see two droplet of plasma suspended simultaneously. And this is just a glimpse of what possible when you learn a controller in real time, physical PD governed systems. In the bottom, this is the example closest to the spirit of our paper, Gene Rebel's active flow control work. That's like two tiny jets on the cylinder lean to suppress the vortex shading in a flow. And the top image show the uncontrolled, the classic Karman vortex uh, street. In the bottom image, the learn policy active and the wake is dramatically smooth. And same physics, different outcomes driven entirely by the neural controller. And these four examples spanning from OD to PD, from RL to DPC to imitation learning, they all share a common idea that I mentioned at the start. An offline trained neural network replacing an online optimizer or a hand-tuned controller. And our paper sits square in this family. And on the next slide, I will step back and give you broader view of how the control field is organized today. Uh, uh, So we have seen what learning-based controller can do. Let me zoom out and give you the honest picture of where the control field sits today so we can see where our contribution lands. In general, we can categorize the optimal control problem uh, into model-based or model-free methods, and model predictive control is a flagship method of model-based optimal control. So if you walk into any industry facility, a chemical plant, a building HVAC system, a refinery, a vehicle control system, and you will find something that Richard Murray at Caltech has pointed out in his optimal control textbook. About 95% of the control loop running right now are PID controllers or hand-tuned expert-driven rule-based logic. And that is the reality of the field. The remaining 5% is our more sophisticated setting I, is model predictive control. MPC is the workhorse of the modern advanced control. It's rigorous, it handles constraints. It has been deployed on everything from autonomous humanoids to chemical plants to autonomous drones to autonomous racing. And you can see in the image here. And when people say the state of the art, like specifically when the control people say state of the art, they usually means MPC. The other side, reinforcement learning, and this is the success story of the last decade in the deep learning world. Wherever you have a reliable digital environment and enough compute to train offline, RL has been spectacular. It's been the engine behind the modern generative AI. It beats uh, world champion at Go. It drives robotic locomotion policies. The caveat in this phrase is reliable digital environment and enough compute, because those are doing a lot of work. And in the real world, building a good simulator is often harder than building the controller itself. And RL requires billion and million of this training rollout to converge. So we have these two dominant paradigm, MPC mathematically principled, handle constraint, but run nonlinear optimization every step, which can be too slow for a large scale system or high frequency control. Reinforcement learning, fast at inference, but expensive to train and sometimes hard to constrain in safety critical setting. Neither of these fit perfectly for the problem we actually care about, which is controlling spatially distributed physical systems, PDE, in real time, where you have physics you can simulate, but you don't want to solve an optimization problem at every time step, and you don't want to throw billion of RL rollouts at it either. The gap in the landscape is what the rest of the talk is about filling. Now let me walk you. Let's make the problem mathematically precise. So, what is an optimal control problem? So, optimal control problem at its core, a very clean mathematical framework. It says, given a system we want to steer and a goal I want to achieve, find the control input that best match the goal while preserving the law of physics and any practical limit that we have. And that's the one sentence definition of optimal control. So yeah, so if let me walk you through the four pieces of the standard formulation, uh, because like every method in the rest of the talk, DPC, MPC, our framework is just a variation of this template. So first we have some objective function. We want to minimize it with two parts. It will have some running cost integrated over time horizon that penalize what we care about at the time instances like tracking error or control effort, and a terminal cost, phi x at the final time, which penalize how far the final state is from where we end up. And the goal is to find the optimal control signal, UT, that minimize this total cost, and which is subjected to the state dynamics represented by this with some initial condition. And says that our control has to be consistent with the physics. Whatever you do with the control, the system should evolve through the physics or through the system's actual dynamics. And third and fourth are basically the state and control constraints. So state constraints say that the state has to stay within some safe envelope. For example, a temperature cannot exceed a critical threshold, a position cannot enter an obstacle, and the control constraints say that the actuator have physical limits. So a motor can only be pushed so hard, or a valve can only be open so far. And in the right hand side, the plot on the right uh, are just the results of this optimal control problem. So the top panel, you can see the trajectory is converging smoothly to the target while the control UT stay within the allowed band uh, mm, between -1 to +1. And that's what a successful optimal uh, control solution looks like in the time domain. And in the bottom is the same plot. This is the same trajectory in 3D space, and the solver has found a path from the starting point to the target that's optimal in the sense of cost and feasible in the sense of constraints. And this is the formal problem. So now, how do people actually solve this optimal control problem in practice? There are broadly three families of approach, and every method in this talk is going to sit in one of these three columns. So on the left, these are like analytical methods. These are the classical tools from the optimal control theory going back to 1950s, 60s, like Pontryagin's maximum principle, which give you necessary condition for optimality and reduce the problem to boundary value problem. And Bellman principle of optimality, which is the foundation of dynamic programming. It says that the optimal solution from any state is the best immediate action plus some optimal cost to go from the next state. These methods are mathematically beautiful for the simple system. They give you exact and closed form solution. But, and this is a big but, they scale badly. Dynamic programming suffers from the curse of dimensionality, and PMP principle gives you coupled differential equation that are often intractable to solve. So for real engineering systems, for high dimensional state spaces, analytical solutions are rarely the tool that you that we actually use. In the middle, numerical methods. These are the workhorse of modern control. The idea is simple. Discretize the continuous time optimal control problem in both space and both time and state, convert it into a finite dimensional constraint optimization problem, and hand it to the optimization solver. And this is the engine that drives model predictive control. And the plot show you a classic example of a numerical optimizer tracing optimal trajectory through the state space, finding the best path subjected to the constraints. Uh, this is what commercial MPC solvers like Kasadi, Gairobi are doing under the hood. Mature, reliable, and well understood. One limitation is computation cost. So solving the optimization problem at every time step can be expensive, especially for nonlinear systems. On the right-hand side, this is the newest branch, the data-driven method. So it's an approximate dynamic programming, and more prominently, the reinforcement learning. Instead of solving the optimization analytically or numerically every time, you train a neural network and agent to output good actions directly based on the experiences. And the classic RL loop, the agent will give some action and the environment returns some state and a reward, and the agent updates its policy. After enough iteration, the agent has learned a policy that acts well without solving any optimization online. Now, here's the important thing to notice. Our paper is going to sit in the third column. It's a data-driven method, and but with an important twist. Instead of reinforcement learning, we treat the dynamics as a black box, which like reinforcement learning, which treats the dynamic as black box and learn from trial and error. We are going to use a differential predictive control, which exploit the structure of the dynamics to train the policy via gradient descent. I'll build up to why that matters over the next few slides. First, let me show you how the MPC, the numerical method workhorse, actually work in practice, because DPC is best understood as a direct response to what MPC does. Let me walk you through the model predictive control in detail, uh, because our work is just adding to this method. And understanding exactly what MPC does makes it obvious why we need something different for PD control. In one line description, MPC has three key pieces. I want to hold on to these three pieces. MPC computes the optimal control inputs at each time step by solving a finite horizon optimal control problem in real time via online optimization. Each of these phases is doing work, but the last one, real time via online optimization, is where the trouble starts in the PDE system. And here is the mathematical problem of MPC solves at each time. It's the same optimal control formulation we just saw on the previous slide, minimizing some sum of stage cost plus some terminal cost, subject to the dynamics, some state constraints, some input constraints. And the only difference from the standard formulation is that the horizon is finite. So we have like n steps into the future, not infinite. And that's what makes it computationally tractable. In the picture on the right-hand side, shows the receding horizon idea, so which is defining the property of MPC. Let me walk you through it. So at current time step k, the controller looks at the current measurement state, which is represented in the orange line. It predicts a trajectory of how the system will evolve in the next time step, uh, which is represented like in this brown color, and it simultaneously compute a sequence of control inputs represented in the cyan color that would drive the predicted trajectory towards the red reference. And here's what the clever part. This is the four step loop that makes the MPC what it is. First, measure the current state, solve the full n step optimization problem. Third, and this is the subtle move, apply only the first control input and then discard the rest. And in fourth, advance one step in time and then repeat the whole process from scratch. So every single time step, you remeasure, reoptimize, replan. And that is why it is called receding horizon. And the prediction window slides forward with you. And the reason of throwing away all the first control inputs, uh, throwing away all the rest of the control inputs, is that the measurement at the next step give you an updated information. So replanning from the fresh information gives you a better control than blindly executing the plan that was made from the older information. And this is genuinely elegant. So MPC handles constraints naturally. It adapts to disturbances because it re-optimizes every steps, and it has strong theoretical guarantees. And it is why MPC is gold standard for advanced industrial control. The catch, which I will show you on the next slide, it is solving an optimization controller every single time step is an expensive commitment, and that's the cost our approach is designed to avoid. So the same slide, but I would like to call out a few things that weren't on the previous slide. First, MPC is not a niche academic method. Look at the tool right now: PyMo, Kasadi, Gyrobi, CVXPy. All these are mature, widely used production-grade software packages. Every one of them is actively maintained, well documented, and used in real engineering practices. If you want to do MPC today, the software ecosystem is rich and ready. So in our experiment later in the talk, we have benchmark against nonlinear MPC. We use Kasadi with IPOPT solver, which is an inter-point method, one of the most respected like open source stack in the space. The second, the challenge, call out in the red bottom, computationally expensive online. This is the issue that I was talking, that you have to do this nonlinear optimization every single step. And for a small OD, for short horizon, modern solver handles it comfortably. But when the system grow, high state dimension, longer horizon, nonlinear dynamics, the per step costs go rapidly. For PD control specifically, where the state is discretized field of 1,000 or 100 of variables, MPC per step time can reach like seconds, and this is prohibitive in the real-time deployment. So MPC is gold standard, but its computational cost is a real barrier for the high dimensional real-time application. Why? In the next section, I will give you a idea about why exactly it is so expensive if we increase it. So I want to show the easiest possible version of it, and then ask what happened when you start scaling up, because the scaling argument is what motivates everything in the rest of the talk. So this is a linear MPC. It's a special case where everything is nice. So the system dynamics is linear and the cost is quadratic, some state and control square with some positive definite weight matrices, and the constraints are linear. As you can see, under this assumption, the MPC optimization is no longer a general nonlinear program. It collapses into a simple object quadratic program, or a QP. So where you have like one matrix H, one linear term, a set of linear inequalities, and this is the best case scenario for MPC. And I'm showing you this because I want you to think like about what easy actually means here in terms of compute. So QP are a very well-studied problem. Our small For a small system, say a handful of state variables, a dozen of control inputs, a predictive horizon of maybe 20 steps, modern QP solvers handle this in microseconds, truly fast. This is why linear MPC is deployed on everything from drone to autonomous racing. You can solve in kilohertz rates on the modest hardware. But let me ask you a question. What matters in this talk? What happens when you start scaling up? If you have 10 state variable, a QP is cheap. If you have 100, it's still fast. 1,000, still tractable, a good solver. But for a PD control, the state isn't a handful of variables. It's a spatial discretization. A 1D might have 100 grid points, and it will scale if you go to 2D and 3D, which you can go to millions. And the QP complexity grows polynomially, typically cubically with state dimension. And that's the best case with linear dynamics. The moment the PDE is nonlinear, Burger's equation, let's say Levi-Stokes equation, Fisher KPP, basically anything physically interesting, you lose the QP structure entirely and you go back to a general nonlinear program at every single time step. A large constraint, uh, nonlinear optimization at every single time step with thousands of million of variables. In PD setting, this is prohibitive. It is why PD constraint MPC are has remained largely an academic exercise and not a deployable technology. So the computation reality is this. So MPC is beautiful for small systems, workable for middle systems, are essentially impossible for the kind of PD systems we care about in real time setting. And this gap is what we are trying to fill. And the answer is to solve the optimization faster. It's not to just to solve the optimization faster, it's to move away entirely to the offline setting and then which bring back to the learning to control idea or learning to control framework. So uh, what happens in the learning to control. So let me make it mathematically precise. Here, the setup, we start with the same parametric optimal control problem we have been discussing, minimize the stage cost and a terminal cost subject to some dynamics and state constraint, control constraint, nothing new here. But notice there are two sources of variability highlighted at the bottom. So the initial state x0 is drawn from some distribution, a family of possible starting condition, and the psi, which we call the scenario parameters, is drawn from a distribution. It collects everything that could change from one instance to the next. For example, reference signals, disturbances, constraint bound, physical parameter. This is just a like a simpler mathematical representation, psi. So we don't have one optimal control problem. We have a whole distribution of optimal control problem indexed by the initial condition and the scenario. Now, here is the key object. If we had a infinite compute, we could in principle solve this optimal control problem at every single possible initial condition and every possible scenario and get back the optimal action for each each one. And that maps from every possible instances to the optimal control is what we call the control solution operator, denoted as pi star. It takes the current state and the scenario parameter and gives you back the optimal uh, control decision. We want to approximate this pi star with parameterized policy, a neural network called pi theta, and theta are the learnable weights. We train them by minimizing the expected cost over the distribution of initial condition and this and a scenario. If we succeed, we end up with a single trained network that at the deployment stage, what it does instead of solving a whole optimization problem, it just do one forward pass and give you the optimal control. And that's the learning to control problem in one formal statement. It's a clean reframing of the optimal control as a supervised or a self-supervised learning problem, where the thing we are learning is a solution operator of a whole family of control problems. And the next question is, how do we actually train the pi theta? What are the different strategies? And that's what I'm going to show you in the next slide. Uh, yeah, so the natural question is like, what should that network look like, or the policy network that we have been talking about? And there are a few standard choice in the literature, and they fall in these three broad categories. First, the direct state feedback is the simplest and the most common practice. The pi theta is just a feed-forward neural network, MLP, or any structured architecture that takes in the current state and scenario and spits out the control action. No solver, no optimization, no iterative procedure, one forward pass. This is what we use in our paper, and this is what most people mean when they say learn controller. And the advantage is speed. The deployment is just a matrix multiply, and the disadvantage is that you lose a explicit notion of the optimization at inference time, which means certain things that like hard constraint satisfactions have to be engineered in some other way. Second is the unrolled differentiable MPC, which is also shown in the plot in the bottom. This is one of the most sophisticated. Instead of replacing the optimization entirely, you keep a solver, but makes it differentiable. You unroll the whole number of solver iteration into a computation graph and treat them as a differentiable layer. So at inference time, you're still doing an optimization, but it's a truncated, learnable optimization with tuned hyperparameter. You get better constraint holding at cost at more compute per step. And third is a hybrid, a middle ground. You use a neural network to produce an initial prediction, say a warm start or a cost vector, and then you pass it through a lightweight differentiable solver. Uh, you get the fast pattern matching of a neural network and a precise uh, and the precision of the solver combined. For this work, we use the simplest of the three, the direct state feedback. A neural network maps the current state and the target control amplitude in one shot and low no inner solver. In the next slide, I will show you two main ways people train this policy, and that's where the choice, supervised and self-supervised learning, becomes important. All right, so we defined the learning to control problem, we picked some policy form, and now the key question is how do you actually train the policy? There are two dominant strategies. The difference between them is the single most important conceptual for in this whole field. Uh, our paper sits firmly on the self-supervised side, but let me explain the supervised learning to control. The first, is also known as approximate MPC or sometimes imitation learning of control. And the workflow is straightforward. You can see in the top left diagram, it shows a slow nonlinear MPC, a solver. You use it to solve optimal control problem offline many times over a distribution of initial conditions. And each of these solution become a label training example. Given the state, the MPC solver decide to give some action. So then you train a neural network, the approximate nonlinear MPC on the right-hand side to imitate this label. At deployment, the neural network takes over the slow MPC solver. It's a clean, uh, simple, and it works. But notice the catch: to generate the training labels, you still have to solve a lot of MPC problem offline. And if the MPC itself is expensive, you are front loading a huge computation bill on the data generation. And your train network is by construction is as good as the MPC demonstration it is trained on. It is always one step behind the teacher. But the second strategy is a differential predictive control, DPC, which is what our paper uses and what Jan and his collaborator developed. Here, the conceptual shift happened. The DPC doesn't need an expert solver to generate training label. Instead, this is a clever idea. So DPC directly minimizes the MPC objectives by backpropagating the MPC loss through a differentiable dynamic model onto the policy weights, uh, and let it unpack that. Uh, so what happens here? So you batch some initial condition references and constraints and some problem parameters. This flow inside the neural policy, which gives some control action, and the control action is fed inside the differentiable system dynamics, uh, and the state is evolved, and then based on that, the cost or the objective function is computed, and then you do a backpropagation using the computation graph to evaluate the or uh, to uh, to train the weights of this policy. So these are the two methodologies: supervised learning to control, learn like to imitate an expert solver. DPC learn by backpropagating the control laws directly through the dynamics. And the advantage of DPC is that it cuts out the need for an expert and avoid uh, the always one step behind problem of imitation. And the cost is what it requires you to have or learn or like the cost is that it requires you to have a learned differentiable dynamic model. For OD system, that's well established. For PD system is generally a hard problem, and the rest of the talk is essentially about how we solve this particular problem. Yeah, so this is just extension of that previous slide, just to explain more about the imitation learning concept, where we have to solve some MPC in the offline stage to generate some data using some using some tool, for example, Kasadi, Pyrobi, or something. And then you try to use some neural network to imitate this. And you will see something that when you train this, you have to minimize the discrepancy between the prediction of the MPC labels. So the plot on the right show a typical result. So the supervised policy and the blue curve track the MPC reference closely, but not perfectly. And the dashed line represents constraint boundaries. And you will see that learned policy mostly stay inside them, but not always. And this is the other catch. When you when you imitate a demonstrator, your policy inherit whatever mistake it makes, and it has no mechanism to recover from them. If the MPC was suboptimal on a particular instance, your neural net will reproduce the suboptimality. You are always at the best as good as the expert. So the supervised approach you has two limitations. Data generation is expensive because you still have to run the MPC 1,000 times, and the learned policy is fundamentally bounded by the quality of the expert. And the whole promise of DPC in the next slide is that you eliminate these both issues simultaneously. No expert, no label, just optimization of the policy against the control objective. So here's the DPC in details. So same pipeline as before. So first we can look at the data set. So if you look carefully, this is a key conceptual shift. So the supervised learning to control, your data set is just a list of state action pairs by the expert MPC. But in DPC, the data set is just a sample point in the parametric space of control. And the plots show what it exactly looks like. Each dot is just one initial condition and one problem parameter drawn from some distribution, no labels. So the training signal is going to come somewhere else entirely from the loss itself. So the second is the architecture where the differentiable and the differential predictive control show up explicitly. The four equation in the slides, the entire method in a compact form. So it's the like the state evaluation equation or some simple ODE system. Second, you have some state, you have some action U, which is predicted by some neural network policy. And third, you have some constraints. And then these all are fed inside some loss function, and this loss function contains uh, it can be your reference trajectory, or it can be some other type of constraints that your control problem require. And it also have these state and control constraints added in the loss term. And what we do, we try to minimize this loss using some simple gradient descent or algorithm or stochastic gradient descent algorithm, and try to train for what the policy. And like in the next two slides, these are just formal definition. I will not go in details. So basically, your problem has become an expectation over an expectation. And that's where basically we are trying to learn over a whole distribution of initial condition and whole distribution of parameter space. And there are specific ways to actually make these constraints differentiable, uh, and which I will not go into the details at the moment. But like if you look at the loss terms also, loss terms are simple. Like you can see, this is the sum over all the possible samples, and this is the sum over all the time horizon. You're evaluating some kind of a trajectory loss or something. Then you have some constraints, and you have the terminal loss, and you evaluate like this. And this is the formal definition of the data set that we were talking about, which are just instances of parameters and the disturbances or initial conditions. So here's the full training algorithm written in pseudocode. I will not going to read line by line, but there are few conceptual pieces that I would like to note. First, the input, the input, we have dynamics, we have policy class, you should have cost, penalty, and optimizer, everything defined. The optimizer is just an atom in our case. So it's a like only non-standard thing in DPC is the loss is optimizing, and everything else is off-the-shelf deep learning machinery. The second is the forward pass. For each sample problem instance in the mini batch rollout, the closed loop system forward for n steps, and the policy propose an action. And then the dynamic advances the state, cost, and constraint penalty accumulate. And at the end of the rollout, the terminal cost, we average over the batch, and that gives you the DPC loss for their iteration. And third, the backward pass. compute the gradient of the loss with respect to the policy parameter theta, and then take the gradient step. That's it, and repeat until convergence. And the output is trained explicitly, uh, explicit policy that you deploy. So the whole recipe in one sentence, same problem, roll out them, compute the loss, backpropagate, update the policy, and it's genuinely simple. And the reason it works, the reason the policy learn everything useful is that the entire forward pass and the policy through the dynamics through the cost is differentiable end to end. The moment one of the pieces become non-differentiable, the algorithm breaks. And this brings us to the central question, like DBC work beautifully for OD systems. So where we have differential dynamics, but it's been deployed in that setting for years. But what will happen if our system is a PDE? Where does this differential dynamic model come from? And that's where the paper contribution begins. So let's start with what we are trying to control. So let's say a general time-dependent PDE with the primary field, and it can be anything like temperature, velocity, whatever physical quantity we care about, evolves according to the differential operator f, which depends on the current field, its spatial derivatives, and a control input ax. And that control input is what we get to choose. The boundary condition, initial condition, and the form of f what specify the physics. And the control problem we want to solve is the same old story: minimize a cost function subject to some dynamics and state constraint. The only thing that is different from the OD system here is that the state is an entire spatial field, not a finite vector, and the cost integrates over the space and time. And the constraint hold pointwise, and the structure of the same problem. So just a state upgrade from R n dimension to an infinite dimensional function space. Now over the right, you will see the DPC architecture, which we spent 6 slides building. Now the question is, like, there is a question mark here. Now because now we don't now we don't have this now the question is, what will be the physical system for this PDEs, because not all the physical systems are differentiable. So there are few answers for this, like, because the different DPC works for the systems to be differentiable so that the gradients can flow through it. It should be accurate. So the policy learn the control for the real physics and not a dream. And it has to be fast so that we can afford the simulated thousands of trajectories during training. Their candidate answer are basically differentiable physics, which are was, I think, proposed from this group. Like, this group it does this coin or differentiable physics, and now I think a lot of different group are working on building this kind of differentiable solver. And the second idea can be the data-driven surrogates, learn dynamics from the simulated data or the data in hand, and we choose to go with the data-driven problem. In our case, where the physics is not known, and we learn a surrogate model, which is a neural operator from the simulated data. And we choose neural operator path, which is a question: what is a neural operator, and why is it the right tool here? Uh, uh, and I will answer that in the next slide. And before that, I would like to give you one slight detail about the control. Is that the control is basically the source is represented by some finite dimensional way. And we parameterized it as a sum of Gaussian basis functions and fixed actuator locations, each with time varying amplitudes. So these match a realistic physical setup where you have small number of local actuators like heater jets and chemical injectors whose amplitude you modulate over time. So the policy output isn't a whole field of A of x of t, it's just amplitudes of this Gaussian functions. With those in pieces, let me zoom in the surrogate model, and first we will uh, ask a question: what exactly is a neural operator? So in the top row, this is what every machine learning person have seen 100 times. You feed a neural network a fixed size input, a photograph of a cat, and say it does its things through some layers, and output the other side comes a labeled cat. and the input is finite dimensional, the output is finite dimensional. It's mapping between two Euclidean spaces and the vector in, vector out. That's the framework underneath 99% of what we call the deep learning today. Image classification, regression, translation, everything. In the bottom row, in our world, PDE, physics, scientific computing, the objects we care about are not vectors, they are functions. A temperature profile along a rod, a velocity field across a fluid, a population density over a landscape. These are infinite dimensional objects. They take a value from every point in the space. So what happened when I want a neural network that takes the whole temperature field, a function over space, and gives back the profile 1 second later? That's not a vector to vector, that's a function to function. And the classical neural network don't naturally do it. So we need a generalization, a neural network whose input is a function and whose output is another function. And that's what the neural operator is. A quick example to ground the idea, because you already know operators, like taking a derivative is an operator. You feed it some function, it gives you back some other function. Integration is an operator. So solving a differential equation is an operator. Initial condition in, solution out, and the solution map of the PDE, given this initial condition and this sourcing term, produces the same state at some later time. So that's exactly the operator we want to approximate with the neural networks. And in the next slide, I will show two dominant architectures that actually implement this idea. So uh, basically, I will talk about first the DeepONet, or the deep operator networks proposed by Lulu. It comes directly from the classical theorem of universal approximation theorem of operators, which say that any continuous operator can be approximated by a sum of some of product of basis function and coefficients. And DeepONet takes this literally. It to have two neural network in parallel. One, the branch which takes the input function and samples some fixed set of basis sensor locations, and the output of vector coefficients. The other, the trunk net, takes query points y and where we want to evaluate the output, and the output vector basis function at the location. So the dot product of these two vectors together, and that's our answer. So the branch gave coefficient, trunk gave basis, and combine them is basically the solution field that we are looking for. Second, the FNO. Uh, uh, so which was coined around in the same time. Completely different philosophy. Instead of two network or dot product, FNO says PD are smooth solution, smooth functions, and naturally described in the frequency domain. So let's work there. A single FNO layer does four things. Take the Fourier transformation of the input function, multiply only the low frequency modes by a learned weight matrix, do the inverse Fourier transformation, and add a skip connection. Stack a few of these layers and you have an operator that live natively in the frequency space. And this work in the principle of integral kernel operator. Basically, you're trying to learn some green functions here. And these two powerful tools, you might be thinking, oh, okay, the problem is solved. Pick one and go. But here's the catch. This is the motivation for everything, and the everything for our work. So both FNO and DeepONet typically train to on a single step prediction. Uh, so input the state now and output the state at later time. So that works beautifully when you have one step. But in a control application, what we actually care about, we want to simulate far into the future to plan your action. So what people do, they use this operator autoregressively, taking one step, feed the output back into the next step, and do this further. And when we do this, we have the problem of this error accumulation through time. And you can, I'm showing this in the plot, as you can see that like DeepONet generally have this accumulation of error, and often have slightly lesser accumulation of error. But this is something that we want. We want a very bounded error over time. And that's why we use time integrated neural operator, which was coined by my colleague Divyajyoti Nayak. So instead of predicting next step directly, we predict the time derivative of the step and let the numerical integrator do the rest of the job for us. And in order to make you understand how the data looks like, so this is so we will have some kind of a initial and some final state, and we will have some random control signals. And since we have these two different type of inputs, we are taking two different branch networks, and we have some trunk network in the bottom. And what we do, we compose it using dot products, and then try to predict what is the uh, derivative of the specific u, and then do an OD solve. In our case, we did RK4 and try to get the next step. And in this way, we try to train for this next step predictions. And when we do autoregressive rollout, we found that it works really well. Now, I think it's time for me to rush through the results because I don't have a lot of time. But the general idea is this. So we have this differentiable predictive control framework. What we do, we train our TI time integrated deep operator networks prior, and then we freeze this network in the next step where this uh, system dynamics becomes the time integrated neural operator, and we train this offline. And once we train this offline, we can actually feed it in the numerical solver to check whether if a policy is trained on this time integrated neural operator, can it be deployed in the high fidelity simulations or not. So I will show you quickly some examples. These is a heat equation where so what we are trying to do. So basically this is an initial condition, and if you evolve the system, it will be like this, the red line. But what do we want? We want to reach this target, the black dot line, as you can see. So what we want to learn some controller for that. So the first step, exactly what we did that I was explaining, we learned TI-DeepONet. And since heat is a very smooth field, we were able to learn it very nicely. We have like a mean absolute error over 3,000 holdout samples of only 1%. And using this, we train our surrogate, and we try to predict or try to get the plug it in our policy in the actual numerical simulation. And you can see the results here. So once you plug in the policy give us some control signals, and it is making sure that the state dynamics is reaching to the target, as you can see. And it have a very and you can see the learned dynamics of this control. So it says that in the initial stage, give a lot of the control, and then when it's reached, you just stabilize it. That's why you have this initial, like a lot of things going on before certain point, and then it just stable because it holds the temperature at that specific location. And when we compare it with the numerical MPC, you can see that we have like almost similar accuracy, and we have like orders of magnitude speed up in our case, because we are comparing like a optimization to one forward pass. So yeah, that was evident. So so there are other problems like burger shock problem, where what was our goal? So let's in Burger's equation, this is an implicit Burger's equation. So if for any initial condition, you will have this tendency of forming a shock. And this curvature is basically the metric that we were looking. What we want a smooth field throughout. So you can see that this curvature is exploding after a certain time, right? And we want to control that. And what we did, we trained the TI-DeepONet, and then learned the policy on this TI-DeepONet. And this have like a 10% error, but at the same time, it was actually uh, it was actually guessing correctly where the shock will form. So the shock was not perfect, but yeah, it was the physics was right. And that's why when you use this controller in the physical simulation, you can see that it is still able to dissipate the shock. And you should look at these curvature plots to understand better. You can see that in all the three different initial conditions, it's like dissipating out, as you can see. And so it's like the accuracy in this case is a little bit lesser than the nonlinear MPC. It's a 1 order lesser, but the compression time is obviously there will be a very high speed up in our case. Moreover, I think the most interesting problem it's a Fisher KPP reaction diffusion problem, where we want to reach to a specific density given some initial density. And here, since we have a reaction, so reaction is continuously trying to make this density go to the equilibrium. So our controller needs to fight against this reaction to make sure that it reaches the specific distribution density that we care about. And same story, we build a TI-DeepONet, very good accuracy, like under 1%, and then we deploy it, the train policy. And you can see here that it almost matched the required density that we want. And the interesting thing is that it learns this continuous oscillation pattern because of the reaction term. So reaction term is moving, continuously moving the state to the equilibrium, and the controller is continuously giving some kind of control signals to make sure that it is on that distribution that we care about. And here, surprisingly, that it is like if you see the variance and the standard mean and standard deviation of the MSE, in this case, it is even better than the nonlinear MPC. Not very huge difference, but it's still better. So, and the time step, obviously, we are reducing a lot in the time step as well. So, in brief, so we came a long way. So, so our method, what we use a pre-trained neural operator in the differential predictive framework, differential predictive control framework to solve a PD control problem, and we showcase different canonical examples where our framework actually do equally good as nonlinear MPC with a high speed up. And the open question here is, like, there are a lot of open questions, like how do we make sure that there are stability guarantees? And there are a lot, like our group is working on with Professor Yan on how to make sure that we have stability guarantees and the scaling up of the same problems into 2D and 3D domain. That's what we did in one work. And there is also a problem of sim to real transfer about how to handle different type of noises when you have partial observation, what exactly we can do. And with that, I would like to thank you all for sticking with me and through this talk, and I would be happy to answer some questions if you have.
Thank you, Divyati, for Dibakar sir, for this very nice talk. Actually, really liked it. You explained a lot of optimization as well, which actually I long back I did an optimization course, so it was a nice refresher as well. Very nice work. So maybe I have a question. Very interesting talk. Um, so effectively, you are actually trying to create a fully differentiable optimization framework where you're creating the control policy also as a neural network surrogate and neural network, right? And then your PD is surrogated by this TI-DeepONet, right?
Yes.
TI-DeepONet, and then you're integrating these two, which becomes the entire loop becomes completely differentiable, right?
Yes, exactly.
Okay.
Yes.
Yeah. So from that point of view, so let's say if I were to compare um, the surrogated TI-DeepONet and run that with the MPC, would that have reduced the cost? Probably to reduce the
Yes.
forward
Yeah.
cost, but not so much about the optimization, I believe.
Yes, exactly. I think there are some work where people do that. So they say that what we are doing, we are trying to speed up the nonlinear MPC. So in order to speed up nonlinear MPC, they don't solve the numerical solution. They use a surrogate model, which is even much faster. And then in that way, they improve the computation cost. So that also, so in that case, so what we are trying to see is, okay, uh, it will not be as computationally efficient as this, but obviously since we are holding on to that optimization, maybe it will be really good. But I believe that if in that case, maintaining this, for example, how to say this plant model mismatch. For example, if the differential solver is a little bit off, for example, in my burgers case, it was 10% off, right? In that case, if you do an optimization on this high error surrogate model, then the optimization might be
Itself
really off. Yeah,
off,
so
right?
yeah, that might be a little bit problem. In that case, we might have to do something more sophisticated. yeah, but people have done this. People are doing this for a long time, actually.
So in this case, if your surrogate model has some kind of a bias, let's say it's
Hmm.
I like the one that you said, the Burger's equation, right?
Hmm.
So in this case, will it be able to kind of get away from that surrogate bias while solving? I think probably no, right?
It so not exactly.
Hmm.
So uh, so the surrogate model needs to be as accurate as possible. If it is very
Oh,
accurate, that's perfect. But in our Burger's equation, what was happening is it was not able to only capture the highest gradient area, right? And so, but it was capturing where is the highest gradient area. That's what the physics tell. So that was working fine for us. So yeah, so we observed that we might not need a very perfect surrogate model for every cases, and that is
hmm.
very problem dependent. Yeah, so yeah, that's what
But
we observed.
perhaps now that you say that, I feel that maybe having this run while you are also having an MPC run sometimes, not all the times, might actually kind
Yeah.
of be
Oh,
the best of both worlds, maybe
yes,
something.
yes. That's exactly like in one of my work, we
It's
are
like a high
doing
fidelity
exactly
and
exactly that.
life low
Yeah.
fidelity kind of thing.
So this method is called projection-based methods. So what
Hmm.
people do here is they have so they they do this open loop thing. They have a policy which gives some action, but when they are going off some constraints, they activate the online
Hmm.
optimization, and then they do the online to make sure that the constraint is satisfied always. So,
Right,
and we are actually working on that, and but at the same time, the scaling issues are there. So
right,
that's
right.
a that's a different problem to deal with.
Thanks. So yeah, others, anybody has any question? So it's a very nice talk. Yeah, Shailesh, yes. Shailesh, we can't hear you, I think. Shailesh, are you there? We can't hear you.
Uh, yeah.
Okay, I think Shailesh might be having an issue with his mic.
Okay.
Hello.
Yeah, now we can hear you.
Yeah. So hi. One second. I think some issue. Yeah. Hi, Dibakar. Thank you for the presentation. It was very nice. I just wanted to confirm one thing. This pre-trained
Mhm.
model is learning PD, right? Simple
Yes.
PD. Yeah,
Yes.
and because its error will affect the whole DPC framework. So, did you explore using maybe physics-informed neural operators in place of simple data-driven ones?
I did not, uh, but people have tried it. So
Oh,
there is a paper which was just published like 2 weeks before me, I think, which like in archive. So they did a physics informed learning to make sure that the physics is maintained. But so our take is, let's say if you know the physics, why not just build a differentiable simulator itself? And that is even much better than building a surrogate again and then do it. But like you can definitely do it, like adding physics, make it regularized well. And if you are able to train that, uh, like pins problem, like which I feel is often harder to train, you can definitely get better results. There is no deny to that. And thank you for adding this point.
Definitely, if you do not know the physics, then that point will
Yeah,
be invalid. But yeah,
yeah,
sure.
true.
Thank you.
Any other question? Okay. So if there are no other questions, then we'll close the session. Thank you, Dibakar, for the wonderful presentation today. Um, and thank you for the audience for being here. We'll meet again next week. Until then, bye all.